Hello everyone, welcome to the second part of the Chapter 2 notes where we're going to keep on graphing a little bit. We've got one more major graph that we're going to look at, which is called a stem and leaf plot. And the stem and leaf plot, as you might predict, it's made up of stems and leaves, but in particular a leaf, notice it's the rightmost digit. And so there's no way to predict ahead of time which digit that's going to be that's in the rightmost, because it depends on what our data are talking about. It could be the ones place or it could be after the decimal, but it's only that last digit that is the furthest to the right on all of the numbers, the rightmost digit. And so the leaves are always single digit no matter what. The stems, they can have however many digits are left after we take away the rightmost digit to make it a leaf. So stems can also be one digit or they can be multiple digits. And the leaves, we write them in increasing order. The idea for a stem and leaf plot is that basically the data are put into some type of an order because we want to be able to tell something about the shape of the data based on the stem and leaf plot. And we've got some instructions here about how we're going to actually construct the stem and leaf plot, but it's pretty straightforward and we'll see by means of an example how to do it. But basically we want to take all of the rightmost digits and put those into a column that's called the leaves, and we put all of the stems, which are all the remaining digits, in the stem column. And we'll just list all the unique stems, and then we will come back through and write down the leaves that go with those stems. And without any further ado, why don't we just try one of these examples. The legend is going to be key to tell us how we're going to interpret the stem and leaf plot afterwards, so that an individual could simply look at our stem and leaf plot and tell what each pair of stem and leaf will represent, whether there should be a decimal or not, and so forth. But what we will do, since we already have our table set up, of course you would be responsible to set up this table where we have the stem and leaf in this kind of a T-chart sort of a situation, and with the legend as well, or else you could call it a key. All that we have left to do is we need to come through these data and look for which unique stems we're going to have. So it appears that our stems are going to go like 6, 7, 8, 9, and 10. Of course we need to have a 2-digit stem here because the 10 is going to count for these numbers that go like 100. And then we need to have all of our leaves. And notice for the ones that have a 6 in the tens place, there's only the one that goes 65. And so the last digit in this case is a 5. That's the rightmost digit, so that becomes our leaf. And we don't have to worry about putting it in order. It's the only one. For the 70s, we're going to have to put them in order, but there are a 1, a 5, and a 7. And we want to be careful about how we're spacing out these numbers as well. We don't want to write bigger in one row than another one because we want to still maintain something about the shape of this. And we're going to talk about how to describe the shapes of graphs here in a moment. But we have for the 8s, and I'm just going to mark out here as we do them because there's an 80, and then we've also got an 81. And looking for if there's anything else, there's of course the 82. Should come next, and then there doesn't appear to be anything until we get to these 85s. So we have 3 of these 85s, 85, 85, 85, and then there is an 89, so we need to get that one. And then what about the 90s? We have a couple of 91s, 2 of them, and then we have also a 92. And we've got 2 95s, a 97, and then a 99. And I think that will do it for the 90s. And then we've got a couple of hundreds. So the hundreds just go 10 in the tens place as it were. And then for our leaves, we have a couple of zeros. In our legend here, what we would want to write for the legend is we could just give an example that 6, we just put this vertical bar to stand for this bar that's separating the stems and leaves. It goes 6. Bar 5 should give us the number, excuse that one, 65. And that's how the legend will go. So we should interpret these stems as being in the tens place and the leaves as being in the ones place. So it will go like 65. And now we can actually reverse engineer our data, for example, by having a stem and leaf plot given to us. So this is a survey. There were 20 20-year-old community college students, and the number of hours they completed are listed over here. And we should look at the legend that basically the leaves are going to be in the ones place and then we can reconstruct the data that are coming from this plot. And so these ones have a 0 in the tens place, and so these are the hours that just go 3 hours, 9 hours, and 9 hours. And then these ones are going to have a 1 followed by the leaf, and so it will go 10, 12, there are 3 12s in a row, and then a 15. And then these ones are going to go like 20 something, so 21, 24, 27, 28. Carrying on, we've got still leaves in the ones place, so we should have a 33, 36, a couple of those, and then a 39. And then we've got some 40s, 42, 45, 45. And then for the 50, see there's no leaf, so that means there was no data point that went like 50 something. But we do have a 63. And these should be all the 20 pieces of data. And following up with that one, there are some calculator steps here. We can use the calculator to make a lot of these graphs for us. So for example, the histograms, we can definitely make them in a calculator. We'll see about using the calculator to use scatter plots whenever we're making scatter plots. We're not going to see that here because scatter plots are specifically for using when we have 2 variables. And so far we've just seen 1 variable at a time for all of these kinds of charts. But I will pull up here. Here's what the calculator is going to look like. We'll just, instead of actually making any of these plots right now, I just want to look at some of the menus that should become familiar over time that we're going to use a lot. And so whenever we have a data set that we want to put into the calculator, we always will go to this button that's called Stat. And the Stat button right here, it has its own particular menus. But let's just see what is inside of Stat. It's going to have Edit as the first choice, and this is the one that we'll go to whenever we're wanting to put in a list of data. And you can see I already have some data input in here. It's possible to clear these by just highlighting the name of the list. List 1 here is representing this first column, so if I wanted to clear out list 1, I could just clear it, say enter, and then list 1 is going to be empty. And it's possible to actually refer to these lists in order to make some kinds of formulas and stuff like that, and that can be very useful as well. We'll see how to do it, but that stuff is all contained in the list menu. So for example, if we went second stat, that will give us this blue list that goes list, and then we can refer to those lists by entering one of these. That would take us to the regular calculator menu like this. Oops, I don't want to have it there. I'm going to quit out of that, and then I'm going to go to list again. See list 1. That's just going to refer to list 1, so we could do something like ask for the average of list 1. My list 1 happens to be empty right now, but what I'm going to do is try to find out, see these have some operations, that's what it means, operations, so we can sort the lists. We could, for example, we can go sort ascending, so that will be in increasing order, or sort descending, so that would put them the greatest number coming first. We could sort lists, like we can say to sort. Oh, and we can refer to these lists by just pressing these numbers as well. The blue going second, and then saying like list 2. We can sort list 2 in ascending order. It's going to tell us it's done, and so if we went back to our stat edit, see list 2 now, it's all in order, going ascending order. That's pretty convenient. We can also do some nifty operations, like we can come over here to the math, and we can ask for example, the average, which is the mean in this case. The average of list 2, we can do stuff like that. It will tell us what the average, if you add up those and divide by how many are there. That's really convenient. And we can also use it to make histograms. You can look here at the instructions that there are for making a histogram. It can save a lot of time if you're having to make a histogram with a lot of data. But this one, I will leave it up to you to try your own example. You can go back to one of the histograms that we made before on these notes and try to make it in the calculator. But what it's talking about as far as plotting one, we should go to the stat plot, which is up here. It's on the y equals, because it's going to graph something, so it makes sense it's with the graphs. We'd go second y equals, it brings up the stat plot. We can turn the plots on and off. And so for example, this one, the plot being on, and then when it says type, this is where you say what type. So the first type is a scatter plot. Then we have some type of a line chart here. This one that looks like a histogram, well, that's what it is. And then we're going to have a couple of other ones in Chapter 3 that we see. This kind of a graph, it's called a box and whisker plot, or sometimes box plot. This one's called an augmented box plot. We'll see about that one, but a couple of box plots here. And then this last one looks like some type of a cumulative distribution thing. We're not going to use that one. But here goes histogram. You can tell it which data to use, for example, but I'll leave it up to you to try that one, looking at those instructions there in the notes. But a couple of last little things to mention about distributions as well. I want to mention this word distribution. This kind of means graph or chart. Graph, chart, sort of a picture of the data. Because we can have the raw data, we can just look at the numbers. But when we're talking about the shape of a distribution, we're talking about what kind of a shape does this data have after we graph them. And that's going to make the most sense whenever we have one of these kinds of illustrative graphs like a histogram. Also, even the stem and leaf plot. We could see, for example, with this stem and leaf plot, it has somewhat of a shape here. You notice how these columns are taller than the other ones. If we flip this on its side, it's kind of shaped like this. It's got a little bit of a long tail coming on the higher values, and the values that have a greater frequency, at least the stems with a greater frequency, they're represented here by these longer rows. And they're kind of bunched up there towards the lower values. And that's what we want to talk about. How do we name these sorts of shapes? Like, what's it called when you have this long tail that's going towards the greater values? And that's going to be called a skewed one. But the ones that are not skewed, that would be called symmetric. Symmetric is the opposite of skewed. And you already know what it means for something to be symmetric. But there's a couple of ways to have a symmetric distribution. You can have the uniform one, which uniform means that all the values are basically just the same. See, like this one, they're all the same. It's not that any of the data are occurring any more than the other values. They're just very uniform across there. Then we can also have symmetry by having a bell-shaped curve where this left side of the graph is a mirror image of this right side. So the outer values, which are the ones, the extreme values going towards the low end and towards the high end, they've got the lowest frequency. And then the values that are towards the middle, they have the greatest frequency. That would be the bell-shaped one, or also bell-shaped. We're going to call something else a normal distribution, and a normal distribution and a bell-shaped distribution, they can almost be used sort of interchangeably. They're not exactly the same thing, and we'll talk about how to distinguish them later. But we'll just refer to this one as a bell-shaped or a bell curve, something like that. And then we have ones that are skewed. When they're skewed, we always name the skewedness as being in the direction of the tail. And so this one has a long tail coming to the left. That means it's skewed left. Or whenever the tail is going to the right, that one is skewed right. And it also has to do with the relationship between the mean and the median, which we'll talk about that a lot more getting into Chapter 3 when we're actually calculating the mean and median. We'll talk about how those are related whenever we're dealing with some skewed distributions. And then our last little section for Chapter 2, which deals with this word, misrepresentations of data. Wow, what a nice subject. In particular, graphical misrepresentations. And misrepresentations are basically having to deal with ethics. I will write this one. You know, data are supposed to be very objective. They're just the raw numbers that you're looking at with the data. And so whenever you make a graph of data, it should also be objective, and it should not mislead people or cause people to come up with inappropriate conclusions. But it's done all the time because ethics are something that a lot of people don't have. And especially when we're dealing with any time that the news or something like that are reporting data, there's a big opportunity for misrepresentations of data to be taking place because people want to put some spin on the data, or they want you to draw conclusions that align with their ideology or whatever the case may be. And through careful use of misrepresenting data, careful use of having deceptive graphs and so forth, it's possible to cause people to draw all kinds of wacky conclusions that your data really do not support. And so this can have to do with people claiming that a graph shows that something caused something else. Like they can say, oh look, for example, a stock price or something like that. People can look at a stock chart and it's got this kind of a shape, and then we can have some kinds of weird behaviors or something like this. And people want to say, oh well, something happened on this day, and so that caused the stock price to crash. But statistics, like we've said before, they don't prove anything. And graphs certainly don't prove that something caused something else. We can only show really correlation. Showing that some things happened at the same time as each other is different from saying that they caused each other. And we can also have some weird kinds of scales that can make the graph look like it's having behaviors that it doesn't really have. We can have parts of the graph be scrunched and other parts be stretched out. And in general, these ones, there's a video right here. It says to watch the video that's assigned to you. At the moment that you're watching this right now, the video may or may not be assigned, but it can be found in my stat lab. A video from section 2.4 if you go into the media that are there available to you in correspondence with the e-text. And also you can just do some research about graphical misrepresentations of data. It's a vast subject and we don't really get to do it very much justice here in this class because we don't spend a lot of time focusing on this one. We want to get more into dealing with numbers. It's a good thing always to be looking out for though. See how people are doing it. And there are whole books written on how graphs can be used to mislead people and which type of misrepresentations are possible. So I would definitely recommend going into some independent study for that sort of a topic. But anyway, that does it for our Chapter 2 videos, and I will see you for Chapter 3.